Hi kids, welcome to the second video in the waves unit called Wave Variables and the Wave Equation. The essential question for this video is what variables do we use to describe waves and what equation shows the relationships between these variables? So just like the last unit, it's going to be really important that you guys get a handle on the variables that we're going to be using to describe waves mathematically. There are 3 of them. The first one is called frequency, and the good news about the wave variables is they're actually words that you've used in your lives, and the meanings that you know probably matches pretty well with the meanings for waves. Frequency is going to be given the variable letter lowercase f, and the definition of frequency is the number of wave cycles every second. The units of frequency are going to be 1/second, the reciprocal of second, otherwise known as the hertz, or Hz. So when you describe a frequency, it's basically saying how many waves are happening every second. Something interesting about frequency is that it depends entirely on the wave source, which means that if you want a wave to have a low frequency, that means the wave source should jiggle slowly. It should only move up and down very few times every second. If you want to increase the wave frequency, the wave source has to change. It has to jiggle up and down more frequently. That makes it an independent variable because it's not going to be impacted by any of the other variables that we're going to discuss. We will have a variables quiz. The kind of question you'll see is given in the example. So, for example, Shaquille splashes the water 10 times in 5 seconds. And you should be able to read that sentence and say, oh, we're talking about the frequency. And in fact, the frequency for Shaquille splashing is 2 hertz. The next wave variable that we're going to be using is actually an old friend. It's velocity, same variable that we've used throughout the entire year. Represented with the lowercase v, velocity is defined as the distance that the wave travels every second. The units for velocity are the same as they were earlier in the year, meters per second, or m divided by s. So the velocity of the wave is how fast that wave pulse actually moves across the screen. So you could measure the distance that wave is covering every second. Please note the difference between this and frequency. Frequency would be how often that wave is jiggled up and down, and velocity is how quickly it actually moves. Velocity is also an independent variable, although what it's dependent on is kind of interesting. It turns out that the velocity of a wave depends only on the medium that it's in. That means that all water waves in the ocean move at the same speed, which is sort of not something people would have expected. Or on a slinky, no matter what you do to the wave, it's going to move at the same speed through that slinky. The only way to change how fast a wave is moving is to actually change something about the medium, which we'll get plenty of experience with. This makes it independent. A sample problem that you might get on your variables quiz would be an ocean wave is moving 50 meters in 10 seconds, and you should be able to read that sentence and identify the variable, which is velocity, and in this case, the velocity would be 5 meters per second. The third and final wave variable that you'll be held accountable for is known as wavelength. Wavelength is represented by the variable lambda, which is sort of drawn as a funny upside down y. And the definition of wavelength is the length or distance of one complete wave cycle. Because it's a distance, it's going to always be measured in meters. In this picture of a wave shown below, one wavelength could be the distance between one crest to the next crest, or one trough to the next trough, or even one spot at equilibrium to the next similar spot at equilibrium. Those distances are going to be the same if the wave is symmetrical. So wavelength is the dependent variable here. The wavelength of a wave depends on the frequency and on the velocity, as we'll discover in the equation that we'll figure out in a few minutes. However, you could be asked to find the wavelength based on a piece of information given to you in a problem. So for example, In a 1 meter long slinky, Maria could count 3 complete wave cycles. So maybe Maria is looking at the slinky shown to the left, which has 3 complete cycles in it, and she knows it's 1 meter long. Maria would be able to determine the wavelength, in this case would be 1/3 of a meter, because one cycle takes up 1/3 of that slinky. The last thing we're going to be doing in this video is trying to figure out what equation is going to determine wavelength. So I'd like to invite you to try a little experiment with me at home. Put your pencil on your paper and start jiggling it straight up and down 1 time per second. So 1 1000, 2 1000, 3 1000, 4 1000. At this point you should have just like a line on your paper caused by you jiggling your paper up and down. Then, if you can, with your other hand, start pulling the paper sideways slowly, you should be drawing a wave. On this wave that you've drawn, one wavelength is going to be the distance between one crest and the next crest. So if you can figure out what a wavelength is, you could label it. Now, let's try changing one of the wave variables and see how our wave that we draw has changed. So in the space underneath your first wave, do the same thing, except this time increase the frequency of your jiggling to 2 times per second. So put your pencil down and start jiggling 1 2 1 2 1 2 1 2 1 2, and then pull the paper at the same slow speed that you pulled earlier. With your new wave, you should also be able to label one wavelength on the wave that you've drawn. Hopefully your drawing looks sort of like this picture shown below. In that top drawing, when you were jiggling slowly, we should have a long wavelength, which corresponds with a low or small frequency. In the bottom drawing, you should have a short wavelength corresponding with a high frequency. This picture, of course, can help us determine the relationship between frequency and wavelength. If you take a second and think about it, you should realize that there must be an inverse relationship between frequency and wavelength, because the higher the frequency, the smaller the wavelength. Now let's try one more little experiment. Put your pencil down on the paper again and start jiggling with your 1 Hertz frequency. This time, don't change the frequency of your jiggle, but as you pull the paper, you should gradually pull faster and faster and faster. In other words, you're sort of increasing the velocity of the wave. Once you've got your wave drawn, you can label one wavelength on the slow side of the wave and one wavelength on the fast side of the wave, so you can compare what you see when the wave was moving slow versus when the wave was moving fast. Hopefully your drawing sort of looked like this. When your pen was moving across the paper with a low velocity, it should have generated a small wavelength wave, and the faster you pulled your paper, the larger the wavelength should have become. So there is also a relationship between velocity and wavelength. Bigger velocity made a bigger wavelength and vice versa, which means that there is a linear relationship between velocity and wavelength. You can use these two relationships to derive the wave equation. This is the only equation you'll be given for this unit, and in fact the last equation for the year, so it's kind of a big moment here. Take a second and combine your two relationships into one equation. And if you do it right, hopefully you'll end up with this equation right here. Wavelength is equal to velocity over frequency. That shows the two relationships that we figured out in our experiments a couple minutes ago. All right, so let's revisit our essential question for this video, which is what variables do we use to describe waves, and what equation shows the relationship between these variables? Thanks a lot.